Today, we're diving into an idea so powerful, so fundamental, that it's basically the operating system for all of modern mathematics. It's called set theory, and it's this surprisingly simple language that we use to describe literally everything, from basic numbers all the way up to the very nature of infinity.
So, here's the journey we're about to take. We're going to start with the beautiful, simple idea at its core. Then we'll meet the genius who used it to wrestle with infinity. After that, things get dramatic. A single tiny question triggers a massive crisis. And finally, we'll see how set theory was rebuilt, stronger than ever, to become not just the language of math, but a playground for some of the biggest questions we're still trying to answer today.
All right, let's jump right in. The most amazing thing about set theory, this grand idea of everything, is that it all starts with something so basic it's almost deceptive.
I want you to really think about this for a second. What if everything, all the complexities of calculus, all of algebra, all of geometry, what if it could all be built up from just one single intuitive little concept? I mean, that's the wild promise of set theory.
So what is a set? Well, it's exactly what it sounds like. It's just a collection of things. A bag of groceries? That's a set of items you need to buy. Your playlist of favorite songs? That's a set of songs. The items inside are called members, or elements, and they just have to be distinct from one another. And that's it. That's the whole idea right there.
And this is where it gets really powerful. A set can hold pretty much anything you can think of. Numbers, sure, like the set of all odd numbers. Concepts, like the set of all primary colors. But here's the kicker. A set can also contain other sets. We use that little symbol that looks kind of like an E to say something is a member of a set. And believe me, this ability to put sets inside of other sets is where all the magic happens.
And just like you can add and subtract numbers, you can do things with sets. The two most basic operations are union and intersection. Union, that's the U-shaped symbol, is just smushing two sets together. You take everything from both and put it in one big pile. Intersection, the upside-down U, is about finding what they have in common. What's in both set A and set B. Simple as that.
So we have this simple, almost childish idea of a collection, but then in the late 1800s, this mathematician named Georg Cantor comes along, and he uses this simple idea to do something absolutely revolutionary. He tamed infinity.
It all really kicks off in the 1870s. Cantor starts to formally study these collections, and his 1874 paper is basically seen as the birth of modern set theory. But he didn't stop there. Oh no. He kept going and developed an entire arithmetic for infinity itself, creating these things called transfinite numbers. He was literally trying to do math with different sizes of infinity.
And this led to his most shocking discovery. Cantor proved that not all infinities are created equal. He showed that even though there's an infinite number of whole numbers, 1, 2, 3, and so on, you could, in theory, count them all if you had forever. But the real numbers, all the numbers with decimals, he proved you absolutely cannot. It's impossible to list them all. There is a fundamentally bigger, a denser type of infinity. This idea just completely blew people's minds.
So Cantor had built this beautiful mathematical paradise. Set theory was on its way to becoming the new foundation for everything. But just when things were looking perfect, a shadow fell. A deep, fatal flaw was found, hiding right there in plain sight.
This was the basic rule everyone was kind of using without thinking too hard about it. It makes perfect sense, right? If you can describe something, say, is a red car, then you can create a set of all the red cars. What could possibly go wrong with a rule that simple?
Well, a brilliant philosopher and logician named Bertrand Russell was looking really closely at this very rule, and he came up with one simple, elegant, and absolutely devastating question that caused the entire system to just collapse.
Okay, here it is. It's a bit of a brain twister, but it's amazing. Russell said, okay, let's use that rule. Let's create a set, we'll call it R. The rule for being in R is this. It contains all the sets that do not contain themselves. You know, most sets are like this, right? The set of all teacups is not itself a teacup. Easy enough. But then came the killer question.
Let's walk through the logic. Let's ask, is R a member of itself? Okay, option 1, R is not a member of itself. Well, if that's true, then it fits the rule for being in R, which means it must be a member of itself. Whoops, okay, option 2, R is a member of itself. But wait, the rule says R only contains sets that are not members of themselves. So if it is a member, then it can't be. You see the trap? We've created an impossible situation, a logical contradiction. The whole system just broke.
So, was that it? Was math broken? Was logic just a lie? Well, not quite. What this crisis did was force mathematicians to be a lot more careful. They realized they had to go back to the very beginning and lay down some ground rules.
And the solution was to move from what we now call naive set theory to axiomatic set theory. That old freewheeling approach where you could just make a set out of any old property, that was the problem. So instead, mathematicians developed a specific list of rules or axioms that tell you exactly how you're allowed to build a set. You have to follow the recipe. No more making up your own rules, which is what led to paradoxes like Russell's in the first place.
The set of rules that ultimately became the gold standard, the bedrock for pretty much all modern mathematics, is called Zermelo-Fraenkel set theory. You'll usually see it with one extra rule called the axiom of choice, so people just call it ZFC for short. This is the solid foundation we build on today.
So, with this new, much more solid foundation underneath it, set theory was finally ready to fulfill its destiny. It became the universal language for pretty much all of mathematics.
I mean, just look at this list. All these different fields that seem so separate, the weird shapes of topology, the complex structures of abstract algebra, it turns out all of them can be defined and described with incredible precision using the language of sets and the rules of ZFC. It's the one language that unites them all.
And its influence doesn't stop at math, not by a long shot. The sheer logical rigor of set theory is absolutely essential in computer science, especially for databases. Philosophers use it to pick apart logic, and linguists use it to understand the deep structure of language. It's just a fundamental tool for thinking about how things are structured and related.
Which brings us to today. Now, you might think a foundational theory that's over 100 years old is pretty much settled, right? Case closed. But that's not true at all. Set theory is still an incredibly active area of research, constantly pushing the limits of what we can even imagine.
I mean, the stuff that researchers are looking at now is just wild. They're studying things called large cardinals. These are theoretical infinities so huge, so mind-bogglingly vast, that you can't even prove they exist using the standard ZFC rules. They use crazy techniques to build alternate mathematical universes just to see what happens. There are even things like fuzzy set theory, where something doesn't have to be just in or out of a set. It can be kinda it.
So think about that journey. We started with a simple idea, a collection of things. It gave us a way to talk about infinity, it survived a crisis that nearly broke mathematics, and it became the language for the entire field. It just goes to show you that even our most basic ideas can hold the deepest secrets. And it leaves us with this incredible question. If this language gave us infinity, what other completely new worlds will it let us discover and describe next?